Let's suppose that we've carried out the observational study of smoking cessation methods. We're trying to determine which method works best: drugs to alleviate nicotine addiction, therapy, combined drugs and therapy, or simply quitting. The explanatory variable is the method, while the response variable is eventual success or failure in quitting. Our study shows that the percentage succeeding with the combination drug and therapy method was highest, while the percentage succeeding with neither therapy nor drugs was lowest. In this example, there is clear evidence of an association between method used and success rate. Can we conclude that the combination drug therapy method causes success more than using neither therapy or drugs?
It is at precisely this point that we confront the underlying weakness of most observational studies. Some members of the sample have opted for certain values of the explanatory variable, method of quitting, while others have opted for other values. It could be that those individuals may be different in additional ways that would also play a role in the response of interest. For instance, suppose older people are more likely to choose certain methods to quit, and suppose older people in general tend to be more successful in quitting than younger people. The data would make it appear that the method itself was responsible for success, whereas in truth, it may just be that being older is the reason for success. We can express this scenario in terms of the key variables involved.
In addition to the explanatory variable, or method, and the response variable, success or failure, a third lurking variable, age, is tied in or confounded with the explanatory variable's values and may itself cause the response to be success or failure. We could control for the lurking variable age by studying older and younger adults separately. Then, if both older and younger adults who chose one method have higher success rates than those opting for another method, we would be closer to producing evidence of causation. The diagram demonstrates how straightforward it is to control for the lurking variable age by modifying your study design. Notice that we did not claim that controlling for age would allow us to make a definite claim of causation, only that we would be closer to establishing a causal connection. This is due to the fact that other lurking variables may also be involved, such as the level of the participant's desire to quit. Specifically, those who have chosen to use the drug therapy method may already be the ones who are most determined to succeed, while those who have chosen to quit without investing in drugs or therapy may, from the outset, be less committed to quitting.
To attempt to control for this lurking variable, we could interview the individuals at the outset in order to rate their desire to quit on a scale from 1 to 5, with 1 being the weakest and 5 being the strongest. Then we could study the relationship between method and success separately for each of the 5 groups. But desire to quit is a very subjective thing, difficult to assign a specific number to. Realistically, we may be unable to effectively control for the lurking variable, desire to quit.
Who's to say that age and/or desire to quit are the only lurking variables involved?
There may be other subtle differences among individuals who choose one of the 4 various methods to quit smoking. And researchers may fail to conceive of these subtle differences as they attempt to control for possible lurking variables. For example, smokers who opt to quit using neither therapy nor drugs may tend to be in a lower income bracket than those who opt for drugs and/or therapy, because they can afford this method. Perhaps smokers in a lower income bracket also tend to be less successful in quitting because more of their family members and co-workers smoke. Thus, socioeconomic status is yet another possible lurking variable in the relationship between cessation method and success rate.
It's because of the existence of a virtually unlimited number of potential lurking variables that we could never be 100% certain of a claim of causation based on an observational study. Observational studies cannot prove causality. On the other hand, observational studies are an extremely common tool used by researchers to attempt to draw conclusions about causal connections. To do this, great care must be taken to control for the most likely lurking variables. Only then can researchers assert that an observational study may suggest a causal relationship.
So far, we've discussed different ways in which data can be used to explore the relationship or association between two variables. When we explore the relationship between two variables, there is often a temptation to conclude from the observed association that changes in the explanatory variable cause changes in the response variable. In other words, you might be tempted to interpret the observed association as causation. The purpose of this part of the course is to convince you that this kind of interpretation is often wrong. The motto of this section is one of the most fundamental principles of this course. Association does not imply causation.
For example, house fires and wildfires cause substantial damage when they occur. What variables might affect the extent of this damage? This scatter plot illustrates how the number of firefighters sent to fires on the x-axis is related to the amount of damage caused by fires on the y-axis in a certain city. The scatter plot clearly displays a fairly strong or slightly curved positive relationship between the two variables. Would it then be reasonable to conclude that sending more firefighters to a fire causes more damage, or that the city should send fewer firefighters to a fire in order to decrease the amount of damage done by the fire? Of course not. So what's going on here? There is a third variable in the background, the seriousness of the fire, that's responsible for the observed relationship. More serious fires require more firefighters and also cause more damage. This model will help you visualize this situation. The seriousness of the fire is a confounding variable. In statistics, a confounding variable, also known as confounding factor, a lurking variable, a confound, or confounder, is an extraneous variable that is associated positively or negatively with both the explanatory variable and response variable. We need to control for these factors to avoid incorrectly believing that the response variable is associated with the explanatory variable.
Confounding is a major threat to the validity of inferences made about the statistical associations. In the case of a confounding variable, the observed association with the response variable should be attributed to the confounder rather than the explanatory variable. In science, we test for confounders by including these third variables, or fourth or fifth or sixth, in our statistical models that may explain the association of interest. In other words, we want to demonstrate that our association of interest is significant even after controlling for potential confounders.
Because adding potential confounding variables to our statistical model can help us to gain a deeper understanding of the relationship between variables, or lead us to rethink an association, it's important to learn about statistical tools that will allow us to examine multiple variables simultaneously. That is, look at more than 2 or 3 variables at the same time. The general purpose of multivariate modeling techniques, such as multiple regression and logistic regression, is to learn more about the relationship between several explanatory variables and one response variable.
These regression procedures are very widely used in research. In general, they allow us to ask and hopefully answer the question, what is the best predictor of, and does variable A or variable B confound the relationship between my explanatory variable of interest and my response variable?
For example, educational researchers might want to learn about the best predictors of success in high school. Sociologists may want to find out which of the multiple social indicators best predict whether or not a new immigrant group will adapt to their new country of residence. Biologists may want to find out which factors, such as temperature or barometric pressure or humidity, best predict caterpillar reproduction. So how can multivariate models help us to evaluate the presence or absence of confounding or lurking variables? Since the difficulty arises because of the lurking variable's values being tied in with those of the explanatory variable, one way to attempt to unravel the true nature of the relationship between explanatory and response variables is to separate out the effects of the lurking variable.
You may have already identified a significant relationship between your explanatory and response variables, and now want to think about whether this is a real relationship, or if instead the relationship is confounded by one or more lurking variables.
For example, here's a graphical association between birth order and number of cases of Down syndrome per 100,000 live births. As you can see, it looks like a linear association where the firstborn in a family has the lowest likelihood of having Down syndrome. With later birth order, up to a fifth-born child, there's increased risk of being born with Down syndrome. This is a statistically significant association when analyzed via a chi-square test of independence, with birth order as the categorical explanatory variable and the presence or absence of Down syndrome as the two-level categorical response variable. Another statistically significant relationship is the association between maternal age at a child's birth and the likelihood that the child will have Down syndrome. You can see here that babies of younger women, up to about the age of 29 or 30 to 34, have really low rates of Down syndrome. Among mothers aged 35 to 39 and older, you see the rates are clearly higher.
Remember, in the case of a confounding variable, the observed association with the response variable should be attributed to the confounder rather than the explanatory variable. We test for confounders by including these third variables, or fourth or fifth, in our statistical models that may explain the association of interest.
In these examples, it's possible that the association between a child's birth order and risk for Down syndrome could be confounded by maternal age. Alternately, the association between maternal age and Down syndrome might be confounded by birth order. Or, both birth order and maternal age might independently predict the likelihood of a diagnosis of Down syndrome after controlling for each other. Here's a graph that answers this question by showing that maternal age confounds the relationship between birth rank and Down syndrome, and that it's really maternal age rather than birth rank that's associated with Down syndrome. Here you see birth order along the horizontal axis. The maternal age groups are along the z-axis. Then on the y-axis, we have cases of Down syndrome per 100,000 live births. If we look across birth order separately for each maternal age group, we see that there really is no difference in rates of Down syndrome by birth order. In other words, once we control for the age of the mother, that is, examine the rates of Down syndrome across birth order, but one maternal age group at a time, there's no association between birth order and Down syndrome. If we look at rates of Down syndrome across maternal age for each individual birth order, we see an upward trend as maternal age increases. So if you look across these colors, this is a great graphical representation where we see that it isn't birth order that is associated with Down syndrome, it's maternal age. In other words, once we control for birth order, there's still an association between maternal age and Down syndrome. Birth order does not confound the relationship between maternal age and Down syndrome. The relationship holds even after controlling for birth order.
Here is another question about confounding. I start with a simple question about an association between an explanatory and response variable. Is the incidence of coronary heart disease greater among men who drink coffee than among men who don't drink coffee? My response variable is coronary heart disease, and my explanatory variable is the history of coffee drinking. If I find a significant association in my data, I will also want to evaluate whether there are other variables that might confound or explain the relationship. It strikes me that some people who drink lots of coffee do so while also smoking cigarettes. So I would like to evaluate if smoking is a confounder in the relationship between coffee drinking and coronary heart disease.
This relationship between coffee drinking and coronary heart disease is the one that we're testing. But we also want to partial out or remove smoking from that association. We want to see if that relationship between coffee drinking and coronary heart disease is still significant after we account for smoking. Here's a Venn diagram that illustrates how our multivariate models will handle this question. Coronary heart disease is our response variable. Our explanatory variable is coffee drinking. Our basic question is, do we know something about the presence or absence of coronary heart disease by knowing the level of coffee drinking in our sample? But we may also know or believe that smoking is related to both coronary heart disease and coffee drinking. So we want to include smoking in our model as a possible confounder in the relationship between coffee drinking and coronary heart disease. Other terms used to describe potentially confounding variable in my statistical model include control variable, covariate, third variable, or lurking variable. When we're looking at the association between coffee drinking and coronary heart disease, the overlap you see in the Venn diagram is what we're testing. We're saying, is that overlap significant? Are they significantly associated? When we add the potential confounder of smoking, we're asking, is coffee drinking and coronary heart disease still significantly associated after we partial out the overlap between coffee drinking and coronary heart disease that can be accounted for by smoking? Because smoking is associated with coronary heart disease and coffee, there's a part of the association between coffee drinking and coronary heart disease that can be accounted for by smoking, the highlighted area in the Venn diagram. What we want to do is mathematically partial that out. When we run multivariate models, we're partialing out the portion of the association between the explanatory and response variables that can be accounted for by that overlap with the third variable.
For this course, we will only be discussing two types of multivariate models: the multiple regression, where our response variable is quantitative, and the logistic regression, where our response variable is binary.
That is a two-level categorical variable.
The question of when is a third or fourth or fifth variable in our multivariate model a confounder is strategically important. If the variable is a confounder when we include it in the statistical model and the association of interest is no longer statistically significant, then we can determine that our original variables had no real relationship. Testing for confounding variables with multivariate models is vital in the testing for true statistically significant associations or real relationships between variables in our research.
If we had run the model with maternal age and birth order predicting Down syndrome, birth order would have been significantly associated with Down syndrome in that first model. Once we added maternal age to the model as a potential confounder, the association between birth order and Down syndrome would no longer be significant.
So we now know that we will use multiple regression to evaluate multiple explanatory variables and/or potential confounders when predicting a quantitative response variable. So how does a linear regression analysis work? Let's start with a simple example.
We imposed our causal model on observational data by selecting our explanatory and response variables denoted by x and y and placed on the x and y axis of a bivariate graph. Let's return to the graph that we made earlier using the Gapminder dataset. Here, we visualize the association between internet use rate in a country and the percent of its population that lives in an urban setting. As you'll recall, we place the explanatory variable on the x-axis and the response variable on the y-axis. So our research question is the rate of urbanization associated with the rate of people who use the internet? As you can see, we also ran a Pearson correlation and found a pretty strong, positive, and significant linear association between these two variables. R equals 0.61. In order to test this model, our first goal is to determine the equation of that best fit line, the line that we created in our graph that shows the best linear fit between our two variables of interest. As you may recall from high school algebra, the equation of a line is usually defined as y equals mx plus b, where x and y are the variables that are on those respective axes. M is the slope of the line, and b is the y-intercept, the spot where the line crosses the y-axis. In our model, we know that internet use rate is our y, or response variable, and urban rate is our x, or explanatory variable. So we need to determine our slope and our intercept in order to define this best fitting line. In statistics, we often use terminology that's a little different from y equals mx plus b. Our symbols y and x remain the same, but we call the slope of variable x the beta sub 1 value, and the intercept of our model is called our beta sub 0 value. These beta values are often called coefficients. Together, beta sub 0 and beta sub 1 times x make up what is called the linear component of our model. In addition, we will always have some error in our data, and so we must include that in our model as well.